Hello everyone. Today we're presenting our project titled AI versus AI Deep Learning for Deepfake Image Detection. The motivation behind this project stems from the rapid rise of deepfake technology, where hyper-realistic fake images are created using generative models like GANs. These pose serious threats across media, politics, and security. The core problem we address is how to effectively distinguish real from fake facial images when traditional visual inspection fails due to the high quality of fakes.
We used the Flickr Faces HQ FFHQ dataset and generated 10,000 fake images using StyleGAN2 ADA, resulting in two balanced classes, real and fake. Each image is 512 x 512 in size and includes a variety of demographics and visual features. The input in our model is facial images, and the output is binary classification real or fake. We also explored a dual input format, processing both spatial and frequency representations to better capture manipulation artifacts.
We began with a simple CNN as our baseline. It used traditional convolutional 2D layers followed by max pooling, dense layers, and dropout for regularization. This model reached 60% test accuracy with an AUC score of 0.61, indicating weak discrimination.
Next, we used VGG16. It is a pre-trained model fine-tuned for binary classification. After replacing its top layers with global average pooling, dense and dropout layers, VGG16 achieved 72% accuracy and an AOC of 0.79, a significant improvement thanks to transfer learning.
To improve further, we implemented dual stream models that process two representations of the same image, a spatial stream capturing textures and facial inconsistencies, and a frequency stream analyzing Fourier patterns to reveal GAN generated noise. This is a pictorial representation of our concept.
We first built a custom dual stream CNN. Each image goes through its own CNN branch built from scratch using stacked convolution 2D layers with ReLU activation for feature extraction, batch normalization for stable training, max pooling to reduce dimensionality, followed by flattening and dropout. Once the features from both the streams are extracted, they are concentrated and passed into fully connected dense layers for final classification. We use softmax for the output layer to give a probabilistic prediction of real versus fake. The model was trained with categorical cross entropy loss, the Adam optimizer, and early stopping plus model checkpoint to avoid overfitting. This model achieved 97% accuracy and an AOC of 0.99, a major leap in performance.
Then we introduced our most successful architecture, the dual stream efficient model. Each image, spatial, and frequency is processed through a pre-trained efficient net, which extracts high-level features using compound scaling. These streams operate independently with no shared weights to retain their unique perspectives. The outputs of both efficient net branches are flattened, then concatenated, passed through dense layers with dropout, and output through a final softmax classification layer. We applied EfficientNet specific preprocessing to align inputs with the pre-trained model's expectations, data augmentation layers for robustness, and a custom learning rate schedule for smoother conversions. This setup achieved 98% accuracy, precision and recall of 0.98, and a perfect AUC of 1. To
To optimize all models, we followed structured training workflows, real-time augmentation, flips, zooms, brightness shifts, early stopping and model chalk point to avoid overfitting, custom learning rate schedules with the Adam optimizer. For the dual models, we implemented custom TF.data pipelines to pair images across streams and ensure consistent batch delivery. We carefully tackled training versus validation loss to detect overfitting and used dropout layers and weight regularization to ensure generalization. For evaluation, we used accuracy, precision, recall, and F1 score, ROC curves, and AUC scores to access overall discriminative power. After performing the comparative analysis on real and fake images classifications, the efficient net model offered the best balance of precision, recall, and generalization, outperforming all baselines. Misclassification was minimal and usually occurred in edge cases. The dual stream approach was crucial to capture subtle GAN artifacts that single stream models missed.
As a team, we've previously worked with CNN architectures and transfer learning and are experienced with image processing techniques such as normalization, noise augmentation, and model tuning. These skills directly supported this project, especially in developing custom pipelines and interpreting complex ROC and confusion matrix results. To conclude, our project demonstrates the effectiveness of dual stream neural networks in detecting deepfake images. The dual stream efficient net model excels with 98% accuracy and a perfect AUC, making it a strong candidate for real world deployment. Here is a list of references. Thank you.